For example, if a helium-4 nucleus tried to fuse with a proton or a neutron, it would form an unstable nucleus that would immediately decay. To bridge this gap and form heavier elements like carbon, oxygen, and iron requires a very different set of conditions found only inside stars where temperatures and densities can be maintained for extended periods, allowing for complex multi-step nuclear reactions. The rapid cooling and expansion of the early universe meant that the nucleosynthesis process stopped after only a few minutes, locking in the primordial abundances of hydrogen, helium, and lithium. The predictions of Big Bang nucleosynthesis are not just theoretical exercises, they are remarkably consistent with observational evidence gathered from various parts of the cosmos. To measure the primordial abundances of these light elements, astronomers look for environments that are as pristine as possible, meaning they have not been significantly contaminated by elements produced later in stars. This often involves observing very old dwarf galaxies or distant gas clouds that show very few heavy elements. For instance, the abundance of deuterium is typically measured by observing the absorption lines in the spectra of light from distant quasars, which pass through intervening clouds of primordial gas. The helium-4 abundance is measured in the gas clouds of the most metal-poor blue compact dwarf galaxies, where star formation has been minimal. Even the trace amounts of lithium-7 are measured in the atmospheres of very old stars in the Milky Way halo, which are thought to have formed from nearly primordial gas. The fact that the observed abundances of hydrogen, deuterium, helium, 3 helium-4 and lithium-7 closely match the precise predictions of Big Bang nucleosynthesis is one of the most powerful pieces of evidence supporting the hot dense early universe scenario